A sample open source voting protocol. In this video I will outline a basic open source voting method using the digital signatures that I described in a previous video. I will be referencing concepts such as digital signatures, hashes and timestamp servers, so if you are unsure of what these are, I recommend you watch the prior video to gain a basic understanding of these terms. Everything starts with the Elections Office public key, let's call it E1. The Elections Office will use the private key, let's call it P1, corresponding to its public key E1 to validate all voting operations either directly or indirectly. The private key PE1 should only be held by one person, like the person in charge of elections. To delegate authority to other elections employees, this person can use private key PE1 to sign a public key of an authorized elections employee as well as a code indicating what exactly they are authorized to do with that key. A record of all these signatures should be available at the elections server for anyone to access. The main key PE1 should also digitally sign and timestamp any revocations of the digital signatures of employees once they no longer work with the government. It also should note changes in what the employee is authorized to do, for example from verifying software to registering voters, etc. Software used in any protocol will access these records and not consider an employee's digital signature valid for any time after the revocation of the signature or for any operation that he is not authorized to do. Things an employee signed earlier than a revocation order will be valid, unless there is fraud. If there is fraud, then a notice can be posted on the server invalidating any key signed by that person or only specific keys signed by that person. The Elections Office private key PE1 signs the public key of the employee responsible for the software. Let's call that public key E2. The software engineer then validates the software and uses his private key PE2 to sign the software. When you download the software, you check the digital signature of the software to see if it is valid. You see the signature was done by the software engineer's private key PE2. You then check the server to see if it is valid. You see on the Elections Office server a valid record of the Elections Office main PE1 key signing the software engineer's public key E2 and assigning him permission to validate software, and you see no revocation order. You then decrypt the signature using E2 and compare the result to the fingerprint that your hash function generated from the software you downloaded. You find they exactly match. Therefore, you can assume the software is legitimate and not from some hacker trying to steal your vote. That is how validation happens for the software. With the software downloaded and validated, let's look at the process of voting. We start with the Elections Office private key again PE1. It is used to sign the public key E3 of an employee who registers voters. Then you as a voter create a public key, private key pair and bring it in with your birth certificate to get registered. Let's call this pair V1 and PV1. The employee signs your public key V1 with her private key PE3. This validates you are a registered voter. Now when it is time to vote, you create a separate public key, private key pair, V2 and PV2. You will create a new one each election. You do this because your public key V2, or more specifically, a hash of it will serve as your identifier on the voter list with your vote. Only you know that public key V2 belongs to you, and since you do not want data harvesters tracking even how individual anonymized voters behave from election to election, you create a new one each election, V3, V4, V5. The reason you create a public key instead of just a random voter number is you want to be able to prove that was your vote if it appears flipped by some unscrupulous elections official. Your private key PV2 is equivalent of the receipt in the elections thought experiment we held earlier. Except the receipt can be forged, a digital signature is not so easy to forge. So you can see how our electronic system is more secure. So when you vote you will use your temporary this election only private key PV2 to sign your vote. Then you will use the permanent private key PV1 you took to the Elections Office to sign your temporary public key V2. This validates that a registered voter actually signed the key that was used to vote. When you electronically send in your vote, let's look at how the vote is validated. The computer receives the vote and runs it through a hash function like SHA-256 to produce a fingerprint. It then looks at the digital signature of the vote and decrypts it with V2 and sees that it matches the fingerprint, so the vote is valid and tied to V2. A hash of V2 will serve as the voter identifier of the vote if validated. The validation process continues by taking the digital signature of V2 and decrypting it with V1 and comparing it to the hash of V2. If they match, the computer continues down the chain of signatures. It takes that digital signature of V1 and decrypts it with E3 and compares that to the hash of V1. If they match, the computer continues. It looks for E3 on the election server and finds a digital signature of it. It decrypts that digital signature with E1 and compares that with the hash of E3 and they match. Since E1 is the ultimate authority key, the entire vote is validated and can be passed to the first list as a valid vote. If any of these signatures had failed, the vote would be rejected because there was no proof it was a valid voter. The error would be sent to the computer software the voter used to cast his electronic ballot. Now let's look at the other list we will be generating, the list of voters. This requires some thoughtfulness to preserve privacy. Ideally, the computer server would just separate everything appropriately and not tell the elections officials administering it anything. And that should be built into the software. But that does not mean the software could not be modified if people were not watching closely what a corrupt systems administrator was doing. So, to better safeguard privacy, we can create one or more entities outside the elections office to tally the vote. This could be in a different office in the government or a private company or foundation, like with a timestamp server. Then more people need to collude to unmask a voter. With the system we are about to describe, both the private foundation and the elections officials would need to collude together to unmask people, and the server the private foundation was using would need to be digitally tampered with in a way election observers do not detect. So, when you register to vote, the elections official will create 3 unique identifiers for each voter. The main identifier will be a hash of common information of your birth certificate. This information will never change no matter how many times you change your name, address, or pronouns. It will be used in a central national database so people cannot register twice or they get caught when they try to use the same birth certificate. You will also need to have periodic checks of records to make sure that no government employee deliberately miskeyed information from the birth certificate, the image of which will be available digitally signed and timestamped in a secure government server. This public voter identification number will be used for the second list of people who voted. You do not use that hash of the birth certificate information because if someone found out the salt used to execute the hash, they could theoretically use brute force attacks to find out confidential information on the birth certificate from the hash. There are only so many hospitals and days of birth, etc. to have to cycle through, and they might know some of the other information like your parents' names. So a brute force attack on the hash to get personal information that can be used for identity theft is feasible. A third identifier, a secret voter identification number, is created for purposes of protecting privacy. This is only disclosed to the election worker who assigns it, the voter it is attached to, and the people who first processed the votes. However, the people who process the votes will not know who it is attached to. Only elections workers and the voters themselves will know that. That is why elections workers would have to collude with a private company or foundation running the vote server to unmask someone's votes. The elections office will never see any information attaching a vote to a voter identification number. This information is only held by the private company. The private company will have no voter identification numbers they can use to link the vote to the specific voter. This information is only held by the elections office. The elections officer who registers you will separately sign with PE3 this secret voter identification number. When you go to vote, you also sign this secret voter identification number with PV2. This basically ties your vote to your identity. However, as I just mentioned, the server on the other end does not know exactly who this secret voter identification number is. That information is held at the elections office. The server will decrypt the signature of the secret voter identification number generated with PV2 with V2 and compare it to the secret voter identification number. Note, in this case there is no need to hash the secret voter identification number before it is signed because the identification number itself is smaller than a generated hash. If they match, then it is a valid vote as they have already validated V2 in the prior vote tabulation step. They also decrypt the signature generated by PE3 with E3 to see that it matches the secret voter identification number. This is to validate that the elections office considers this a valid voting number. Then that secret voter identification number has a true value put beside it in the database column labeled voted, indicating that person voted. Then the server takes both of these digital signatures and the public keys they are associated with no other information and puts them in a document. Note that since E3 is available on a public server, there is no need to store it. This document is then encrypted with a traditional symmetric algorithm. These are the algorithms where the same key can both encrypt and decrypt the document. It uses a random key we will call K0. K0 is produced by taking 3 randomly generated 256-bit codes, K1, K2, and K3, and performing an exclusive OR operation on them to produce K0, which will be used to encrypt the data. The three codes used to generate this are then encrypted with E4, E5, and E6 respectively, the public keys of 3 elections board members. Then only the encrypted data is kept in the database, with everything else discarded. The same thing will be done with the signature generated by PV1 of V2. In this manner, only the elections officials who have access to PE4, PE5, and PE6 can unseal these records in case of a protest or audit. You can have more than 3 people, say 7 or 10, or generate combinations of encrypted files where say 5 of 7 members of the board would need to authorize the record to be unsealed. After the election and all challenges, this data is securely deleted as defined by the voting laws. This is reasonable protection of privacy with a provision to unseal records if a discrepancy is found in the initial vote and voters lists. You can then try to determine at what point the system failed. Was the data correct in the server but crooked election officials just flipped votes? Did the server improperly validate records? There should be time-stamped returned records to the voter so he or she can prove the records were properly sent and received. Additionally, all registration actions should be visually recorded from at least 2 different camera angles and digitally signed and time-stamped. This way, if someone was registered who should not be, you can look at not only the digital signatures to see who registered the person, but you can also see if the person registered someone who did not even look like the person who they say was registered. When you have proper auditing with digital signatures, timestamps, and video, the incentive to commit fraud goes way down because it is a lot more likely someone is caught in the process. You can also use the information to reconstruct an accurate voting count without having to completely revote as you might with a paper ballot system that we described in an earlier video. Which brings us to the last stage, publishing the results. Both lists, votes and secret voter identification numbers, are sent back to the elections office. The elections office then replaces the secret voter identification numbers with the corresponding public voter identification numbers and information about each person to be published on the first list of who voted. With the second list, the public keys like V2 are hashed and then turned into diceware words. Words are easier for humans to validate than strings of hexadecimal codes. These are then listed next to the corresponding vote and the digital signature confirming that vote. The public key corresponding to that signature will not be displayed publicly, but will be on file with the elections office. These election files for every vote cast will be digitally signed by E2, E1, or some other authorized elections official and distributed. Everyone can then use this data to confirm the vote count, confirm the number of voters matches the number of votes, confirm their votes, and look for people they know to see if they voted when they should not, i.e. dead or comatose. This way, everyone counts the vote. If someone got hacked, they will know. If elections workers flipped votes, people will find out about it. The other thing you can do is have the election software install a background task that checks for the publication of the results and has access to the hash of the public key used to vote and hash of the raw vote file for each member of the family that voted with the software. Then everyone's software automatically checks and warns people if the vote was counted improperly. With our hypothetical example, not everyone realistically might be paying attention. But if everyone is running this software, everyone is checking and being warned. If there are discrepancies, people can then use their time-stamped votes to file a challenge with the elections board. And if the vote totals are wrong, everyone is going to get a warning. I would also add real-time notifications of voting from the elections office. After you have voted, not only should the software confirm that, but the private company receiving the vote should send an electronic message to the elections office of secret voter identification numbers as they come in. For security reasons, you might not want to have direct communications between the server accepting votes and the elections office, but you could have someone run over a digitally signed thumb drive of all the secret voter identification numbers voting that day at the end of the day, and then that could be processed to send out a message that we received your vote. This way, if someone somehow got access to all your private keys to vote and tried to vote in your name, you would know about it in a timely manner instead waiting until after the publication of the initial vote tally. One other piece of information will be added to help with verification. Before submitting a vote, the voter will be asked for a secret password only they know. It can be anything they can remember. They will sign this with PV2 as part of the vote record submitted. This will also be published in the files generated and on the website. With this, a person can just search the published results on the website to look for this code and verify the vote file next to it matches how he voted. Scraping software should be used by independent elections monitoring organizations to verify the published web results match the digital signed raw files. You do this in case their election software was compromised. Hacked software could verify their votes when it was not accurate. Manually choosing a password and then manually looking for it will bypass any and all computer manipulations in checking your vote, even if your computer was hacked. As you can see, this system is really robust. The computer can perform complex election counts like ordered choice voting. Each step is audited and confirmed with a chain of digital signatures. The most likely point of fraud is election workers messing with the voter rolls to create fake voters. But that same problem is going to exist with any system of elections you have. With this method, people can see who is voting in every election, and you will have video of each registration that can be used in cases of contests, but can also be periodically audited internally and externally to prevent fraud. This is probably as secure as you can reasonably get. I will address the threat of quantum computers and hacking in other videos and some additions to the protocol to mitigate these threats. But with this open source count, everyone can monitor the result. This system is designed to identify such fraud just as you would in the 2 whiteboard count example. Except this is better because you will have automated checks from the software side even if a lot of people are lazy. And if there is a virus in the wild screwing with software, it will be identified when people who are diligent find their vote altered on the elections website, and they notice that the software is not identifying the error. Then a broader alert can be sent to all voters along with instructions on how to check your computer for the compromised code. The biggest issue will probably be with the people coming into voting centers to vote because they do not have a computer. This will run into the same issues we have with black box voting systems today, as these machines could be corrupted by partisan elections workers. The use of old-style read-only DVDs with a bootable open-source operating system along with a validated fingerprint of the entire DVD image is probably the best we can do to prevent such problems. The DVD can then boot computers and run the software from the DVD. In fact, all elections software should be run this way for best protection against rogue software on machines and people trying to gain access to private vote data. I will speak more on this topic on the video on mitigating hacking. Either way, the people without computers at home should go out of their way to get access to a computer to check their results, and the government and public interest foundations should find ways to facilitate this. Again, the final check of the votes is the best deterrent to all attacks of this voting system. As long as enough people carry those out as part of their civic duty, systemic voter fraud should be eliminated.